different. You will rue the day you decide. No, okay. So welcome to the optimization and data science. Thank you, Bernard. Welcome to the optimization and data science workshop. So first, I'd like to introduce Peng Zheng, who will be co-teaching it with me. So the way we're going to do this, yeah, stand up and say hello, Peng. Sorry, yeah. There we go. So the way we're going to do this is first Peng will say a couple of words about the software component because he's prepared some examples. So since this is a workshop, it's not just going to be kind of lecture. There'll be like a sort of a lecture format followed by an interactive. First hour, you'll just be running some things, and Peng will explain how to install them. And then after the break, once you've acclimated and installed everything, you'll actually have a chance to do something as well when we go on to hours 2 and 3. So in the 3 hours, we'll talk about the role of optimization in machine learning and data science and kind of do it in an old school kind of way with some board work and modeling, emphasize the role that algorithms play in everything. So over the 3 hours, we'll cover some basic statistical modeling, focusing on classification of MNIST images examples, some non-smooth optimization, and also some non-convex optimization for robust applications. So you'll have some intro view to these things. So just as a quick survey, how many people have taken an optimization course before of any sort? Great. How many people have implemented algorithms for, say, learning, like gradient descent or something like this? Wow, so you're like very well prepared. Okay, so let me hand it over to Peng, who'll tell you a little bit about the software.
Sorry, guys, can you see so this, today, I think we're going to go through there are 3 parts as I said. So there are 3 parts talking Jupyter notebooks. It goes for a year, and then in the afternoon, I think you will be really have an easy time with Brandy's Jupyter notebook class. But maybe just go, if you have your computer with you, just go type in this command, then the material will be there. There are 3 Jupyter notebook, there are 2 PDFs for something to be very part of is that big enough? Yes, and then there are 2 PDFs. First up to the book chapters that will go covers briefly today, and then there are essentially there are a data set inside it, it's part of the MNIST data. So we'll just run some examples on the data set. So if you guys have time, maybe just download this. So we're going to use Python today to do the software. So how many of you guys know about Python or have some experience? Really, let's see. Originally, we're actually doing this in Juliet, and then it's not it's not that a good responded. So make sure that you have NumPy, you have SciPy, because we use one of our functions in SciPy, and also plumbing the MATLAB. So then you're all set, and we'll go through that when we finish the first part.
All right. Great. So let's stop. I think there should be a pause. Projector hide. Yes. Okay. All right. So we start off with some pretty basic kind of philosophical ideas. So I hope you'll bear with me, but I'll sort of try to use this to make a particular point. So hopefully it won't be too boring to you guys because you've already seen a lot of things. So when we talk about kind of data science, when we talk about data science, we think about answering some questions which is informed by data. So we'd start with some application or question. we start with some application or question that we'd like to answer. The one that we're going to be focusing on throughout the 3 hours is just classifying some images, whether you're seeing a 0 or 1, a handwritten 0 or 1. How many people have seen the MNIST data set before? Okay, great, about half of you. So we'll be looking at that example. So the application or question for us will be like, can we automatically figure out whether we have a handwritten 0 or 1? Whether a scan digit is a 0 or a 1. So it's a pretty straightforward problem. So the application, the question, and then we all understand that since it's data science or machine learning, there's going to be some underlying set of data from which we're going to be able to learn something in order to answer this question. So there's going to be some data box here. So for the particular 0-1 classification question, all this data is going to be it's actually going to be pixelated handwritten images. So each image is going to be 28 by 28 pixels, and then it's going to be somebody's really poorly written 0 or 1. So these are the two 0, 1 kind of images that look like this. So there's going to be lots of those, and then there's going to be associated to these, there's going to be labels. Oh, this is why we have lots of pens. Also, I'm moving around because the room is cold, so this gives me an excuse. So try to be really excited to warm up the room. There's going to be labels. The labels are going to be, this is a 1. And this is a 0. So we know that the image corresponds to the label. We're going to have a training set of those. And from that, we're going to want to somehow learn to automatically distinguish. And so the thing that enables us to do that is some kind of model. So in order to come back and answer this, it's going to get a little bit cramped. We're going to have some kind of model box. So we're going to derive the model kind of from this thing from scratch and then kind of show how it extends generally. But then you all know this since you've had optimization classes, but one other thing that we need in order to take the model, which kind of connects the application to the data, there's going to be some algorithm that's going to fit the model. So before we really get to the end, there's going to be some algorithm. It's going to be some algorithm, which is, for a lot of these applications, an optimization algorithm. That's going to allow us to actually answer the question, i.e. train the model, figure out what the parameters are, and then from the parameters we can then answer the question. So one thing that I'm going to kind of drive at today, and we're going to show you in the 3 hours, is that there's a very close relationship between these two things in the whole picture in particular, where if you invest in knowing about different algorithms and models, there's kind of more that you can do. Because people sometimes think of this as just a secondary thing, like the model is the primary thing. Once you know what the model is, what the data is, you just kind of learn it and that's it. But then snags come up. So snags might be something like you have outliers in your data. That's an interesting example. Maybe you have poorly written images and you don't want to train on those, much more serious in other contexts. Or you want your answer to have a certain kind of structure. Like, for example, you want to have a simpler classifier, you want some kind of sparsity. How many people have seen anything related to promoting sparsity in regression or classification solutions? Okay, so that's so whenever you want extra things, extra properties, or getting around extra difficulties, that's going to change the model, and then the model becomes harder to solve, so the algorithms change. So you want to kind of learn these things together and do a lot of algorithms to be able to overcome those challenges. So that's kind of what I want to drive at. So I want to bring the focus of the algorithms back into the picture, not think of them as some kind of third-party thing we just call gradient descent and that's it, even though gradient descent is one of the things we're going to talk about. Any questions or comments so far? Okay, so now we're going to go quickly. Let's just figure out, for this exact example, we're going to just derive the model by hand that connects the data to the question. Okay, so we're going to start we're going to start, we're going to say, okay, we're going to say, so we have a bunch of, so we're going to call our labels yi. So yi, and this is going to be just in the set 0 and 1. We're going to call labels yi, and then we're going to, for each label, we're going to think of probability pi that label is a 1. Okay, and then from here, we can write down a likelihood model straight up for observing any data point that we saw. We can write down the chance that we saw a 0 or a 1. So the likelihood model, the probabilistic term, is going to directly be pi to the yi times 1 minus pi to the 1 minus yi. Okay, so it's pretty clear. So if you take yi to be 1, then the chance of seeing that is pi, and then this term disappears, just becomes a 1. And if you take yi to be 0, this term becomes a 1, and so with chance 1 minus pi, you're going to see a 0. Okay, so this is what we call the likelihood of seeing yi given pi. So this is for every single set of images and labels that we have. Okay, so this is a basic thing. And one key observation that we make here is that all of these are independent. So once PIs are given, these terms are all independent. Okay, so in other words, if I tell you what your chance is that a particular image is a 1, you don't care about any other image. You can directly figure out what the likelihood is of actually seeing what you saw. Okay, so this is going well so far. So this is a probabilistic model. It's a good start. It's a little bit disconnected. It's talking about zeros and ones and probabilities, but the missing link is there's a disconnection between the data that we actually have and that model. So the thing that we're going to need to do to really write down some kind of formulation to solve the problem is we're going to need to connect the two, but we're not there yet. So before we connect the two, I'm actually going to take the log of this thing. I'm going to mess around with it a little bit more. I'm going to go a little bit fast because we're short on time. But you can do this, if you have questions, you can discuss it over the coffee break. So I'm going to go a little bit fast. So I'm going to look at the log of this thing. I'm going to take the log of this thing. If I take the log of this thing, I have yi log pi plus 1 minus yi log 1 minus pi. And then I can group two terms together. So I've got a y log pi minus y log 1 minus pi. So I can write this as yi log pi divided by 1 minus pi. And you're all alums of the applied math department and, other faculty students. You guys are all good with this. And the only term that's left over is minus log of 1 minus pi. So that's the term that we get. Yeah, all right, thank you. Plus log of 1 minus pi. So now there's something interesting that happens here. So this term is based only on the parameter. So there's only pi that appears. And here you have the pi, a term that's based on pi, but then you also have the data. And just by some convention, I'm kind of deriving for you a general linear model approach from statistics. By convention, we want the parameter that we're actually going to use in the problem, we want that parameter to be just multiplying the data in a linear way. So we actually do at this point, before we keep going, is we just define theta I, define that thing to be whatever appears here and multiplies the data. So it becomes log of pi over 1 minus pi. Okay, and if we do that, then there's going to be a backwards relationship, so we can solve for pi in terms of theta I. So pi is going to be E of theta I divided by 1 plus X of theta I. Okay? It's really confusing. You know what's confusing is that the top board is the bottom controller. That's why I'm having so much trouble. Okay, so then we're just going to keep going. We're going to keep going with this. So if we plug everything back in, we can now write a log of the likelihood of yi given theta I. What's that going to look like? Well, that's just going to be yi log theta I, yi theta I by definition. That's what we were after. And then we're going to have minus log of 1 plus x of theta I. And that term is what you get when you actually take the expression for pi and you stick it into that log. So that log of 1 minus pi just becomes log of 1 plus x of theta I. So it's a little algebraic exercise we're going to skip. But I just want to make sure you guys all believe me. Okay? So basically, all we've done now is we've played with the likelihood a tiny bit, so we have a different parameter. Instead of pi, we have theta I. And now we do the final thing, which is that we're going to link now this theta I. We're going to link the theta I to the data. So what we're going to think about, so who knows what the next step's going to be for the image, for the 0, 1 images? What are we going to do to the theta I's to kind of link them all together? Yes? We're doing it. We're definitely doing maximum likelihood. But what is? I'm looking for that precise link. Like, how are we actually going to know whether a new image that we're getting is going to be a 0 or 1? What are we going to do? Yes. Oh, yeah, I think I'm asking. So I'm fishing for something very specific, which is a bad idea. So we need to translate those images into something that's going to be useful to us to connect everything together. So we're going to take each image. So let's just pretend I have an image right here that looks like a 1, and then we're going to. So this image is 28 by 28, right? So I'm going to slice it down so that it's a bunch of columns, 1 by 1 columns. I'm going to slice it. I'm going to slice it in blue rather than red. So there's 28 columns, each is 1 by 28. And then I'm just going to vectorize it. So then I'm going to have a vector, and that's going to be my input. So I'm going to take each image, and I'm going to translate it into a vector of numbers. That's 1 by 728. Okay, and then each column is going to go into each respective slot. Does that make sense? So that's how I'm going to translate the image into some input I can use to go into this model. So I'm going to call this thing AI. So that's going to be my feature. So I've generated features from the images in the stupidest way possible, just vectorizing the whole thing, but at least it's very clear, right? And this is exactly what we're going to use in the example. So now what I need to do is I need to link the theta I's to the features I generated, and I need to bring in model parameters that we're going to optimize over, so we actually have the whole thing fitting together into one whole. So what I'm going to make is now I'm going to make an assumption. So here's my assumption. I'm going to say theta I is equal to the inner product of the feature AI and X. So each of these is specific to the images. And the X are the model parameters. So these are model weights that tie everyone together. Okay? So that's an assumption that we're making. That's an assumption we're making that's linking everybody together. So now we're going to do exactly what somebody said, maximum likelihood. There's a lot of people. We're going to use maximum likelihood. So now we want to maximize the likelihood over X of all the observations. Okay, and so there it is right there. So we're going to, instead of maximizing the likelihood, we're actually maximizing the log likelihood, because log is a monotone function. If one number is bigger than another, its log is bigger than the other's log. Okay, so we just maximize this. So we maximize over x. We plug it in. So we have sum. I goes from 1 to n. Well, this is the number of images and labels. Yi aix minus log of 1 plus exp aix. Okay, we're going to maximize that over x. And actually, and this is like purely because I'm OCD, I can't, just doing optimization, just write everything in min form, just can't handle the max. So I'm just going to change the sign and minimize. Okay, just have to do that. So actually going to minimize the negative of this thing. Okay, and that's it. So this is now the problem that we need to solve. When we solve this problem, we're going to get a parameter vector x, which is also 1 by 728. So it's going to, the x is going to be exactly the same size as my features, but you can also reshape x and get something that looks like an image, so we'll actually be able to interpret the x, right? And the idea is that the x are the common weights that you take pairwise products with, sum it up, and then if the number is big, it's a 1, and if the number is small, that's a 0. Okay, and we derive this thing completely from scratch, just starting from the binomial model of a coin flip, and just adding in this little assumption that the parameter theta I that appears to multiply the data, that this thing is connected just through a linear model. Yes? You have to yell.
Can you repeat what we did? Is that how, like?
Yes, x are weights that we are introducing x as a decision vector of weights. So we're introducing them. So the x we're going to take a weighted combination. So you're going to take a picture of a 0, 1 and send it to me, and I'm going to vectorize that thing. I'm going to take my x that I learned, take the inner product, and if it's big, I'm going to say, Laura, that's probably a 1, and if it's small, I'm going to say it's probably a 0. Okay, so that's the stuff. So this is now an optimization problem. So we're actually doing well. So now it's got this optimization problem. It has a linear part, and then it has this slightly different thing that's coming from the data model that we've assumed. Okay, and this process that we did is very, very general. So I'm just going to, before we go on, because we're going to continue from this point with the optimization aspect, now that we have a problem to play with, before we go on, I'll just tell you kind of how general this whole thing is, because, why not? Yeah. So we could have had so in general, you can have any connection between the data and the model. So let's just say between parameters theta I and observations yi. So I'm going to simplify this because, just to keep things a little bit nicer. But let's just say we can consider that the function, that the likelihood of the observation given theta I is given to you is proportional to is proportional to some exponential model. So it's proportional to the exponential of yi theta I minus some function g of theta I. So this is a really simple generalization of what we, where am I pointing to, of what we actually saw happen. So for any model like this of observation given theta I, if we follow the same modeling process, we end up with the problem minimize over x. I'll just write this as y transpose ax. Okay, so there's going to be a linear part that mixes together so this A part is just I'm taking all the rows AI and I'm putting them in like this. Okay, and here the AI. So this is not part of the sum. It's always there, regardless of the form of the f or the g. And then this is the meat of it. This is what connects your specific probabilistic or statistical model to the data. You have a question? Yes, yes. The question is, can I give an example of this more general thing? And yes, absolutely. That's kind of what I want to do. So I want to give you 3. So the very first one is linear regression. We didn't start with linear regression because classification is a little bit more fun, has more of a machine learning feel to it. But linear regression is a fundamental thing that we all do all day, every day. So for linear regression, you just take your gi of theta to be equal to 1/2 theta g of theta I, is 1/2 theta I squared. If you take that to be your g, then this thing right here just ends up being minimize over x, 1/2 norm of ax squared minus y transpose ax. And this is a constant away from minimize over x, 1/2 ax minus b quantity squared. And that's exactly the linear regression that you all, I assume, know and love. Okay? And then if you take a second example is if you take g of theta I is equal to the exponential function, then what you end up with is Poisson regression. Poisson, so for count data. Poisson regression for count data. So for example, if instead of having images such as zeros and ones, your data are actually the number of phone calls you're getting from your friends, and you want to know, can you learn the number of phone calls you're going to get as a function of the day of the week it is, how close the midterm is, that kind of thing, then you would use this model to link the data to the. So basically, if you have count data, you could use this function. If you have direct observations, continuous data, you can use this function. And then the third example is the one we already did, where for our case, for logistic, g of theta I is equal to log of 1 plus exp of theta I. And this thing we derived, so I don't want you to feel like it's some kind of magic. We just derived it by writing down the probabilistic model, and we can do that exactly the same way for these things. It's kind of a general way to construct the connection between your data and the parameters, and the end result's the same. Okay, so this is doing okay. Any other questions? Yes? So question, how do we formulate lasso regression? So so let's now that you guys understand this, let's go back and talk about the consequences a little bit. Did I just? Yes, and now the bottom one. No, the top one. this is the most confusing thing ever. It's just, no matter how many times you do it, it's just really hard to learn that the top one is the bottom and the bottom one's the top. Ah! Okay. Okay, so there's the overall likelihood problem we got for doing the logistic regression. So there's now things you can do to this. So this function is coming from the statistical sort of statistical probabilistic model. Okay, when you look at the statistical probabilistic model, the term log of 1 plus x comes out naturally. So when you want to impose additional information, then you're going to start adding information directly to the x. So once you have your optimization formulation, you can modify it to include prior or additional information. And we're going to, I'm going to not answer your question in detail since we're doing this in the second hour, but for the lasso case, you can just add the sparse regularizer to your problem. And we'll talk about why this happens. If you know that your x should be bounded, the weights should be between 0 and 1, you can also instead add such that x is between 0 and 1. Okay? And all of this is pretty easy to handle, but then you want to have a handle on the algorithms to do that so that you know that it's easy to handle, right? So you can confidently go and add that information. So that's kind of what we're talking about. Does that makes sense? So, but now, before we get into adding any additional information, so this is next hour. Okay, next hour. So before we get into any additional information, let's just talk about optimizing this thing. So we mentioned linear regression already. So linear regression is super, super special. It's sort of, you learn it first, but then it gives you the wrong kind of feel for the world. So you learn that linear regression is minimum of x 1/2 of ax minus b squared. And you learn that you can take the derivative and set it equal to 0. And so you learn that you can find x least squares is equal to A transpose A inverse A transpose, I'm going to say y instead of b. It's been using y. You can find a closed form solution. This thing is special only to the unconstrained least squares problem. Period. There's no other problem that can do this, and you can't even do this for large-scale least squares problems. You know, your A, you may not have an A in your hands. You may never be able to form A, let alone A transpose A, let alone invert it. So essentially what you're going to end up doing is doing some kind of iterative method. So then you start thinking about iterative algorithms for solving that problem. So we're going to get into iterative algorithms for solving this. So you just can't do it without iterative algorithm. So an iterative algorithm for solving this is everything is smooth. So you can essentially just implement some kind of down the hill. We'll look at downhill methods. So we're just going to take gradient descent. So this is a start. So we're going to start at some point x0, and then we're going to keep stepping. And the general pattern is going to be xk plus 1 is going to be equal to xk minus some step times the gradient of that thing. So the gradient of that thing, I can actually write it down in closed form. So it's sum I equals 1 to n. So I'm going to write it in terms of the g, just so I don't have to, because Peng will give you the details here. So it's going to be g prime evaluated at aix, g prime evaluated at aix times ai, and then minus aiyi. And the x is the kth iterate. Okay, so this is the next step. This is the current step, and this is the gradient of the formulation. So this is your first, very first iterative algorithm that we learned. So the only question that we need to answer, and I'll answer in the next couple of minutes and then hand it over to Peng, is how do you set the step with which you go to make sure that you're always heading downhill? Okay, so this, yes? Yes, that's a good idea. So there's a gradient descent. So if we switch over, just go a little bit more abstract so we don't drown in the details. So we look at minimize over x, f of x. So then the algorithm is xk plus 1 is equal to xk minus alpha grad f at xk. And then I was just going to a lot of work to plug in all the details for you for the logistic regression case. So now I'm just saying we need some way to figure out what that alpha is. So just give you a little bit of a flavor of that and hand it over to Peng. So let's just say that our problem that we're solving looks like this. Okay, so I drew that to be non-convex just so you don't get the wrong idea. And say that this is our current point, xk. So current point, xk. So we have this kind of a tangent line. So we can use to understand gradient descent and the alpha is we can get global quadratic upper bounds that are tight at the point. So it's a cool fundamental algorithmic idea. So I'll draw it for you. So all we do is we figure out some way to get global quadratic upper bounds, which is something that looks like this. So the blue dotted line, it is tight at this point. It's tight at this point. It is globally above the function. So this is my function f of x. And this is some function m of x. And what I want is I want m of x to be greater than f of x everywhere and equaling x at the point. And then I have the nicest thing ever. So then I have, what do I have? I have that, so suppose I can find a function for you, a function for you that looks like this, a simple bound m of x that's always bigger than f. What's a simple intuitive strategy for doing optimization then? Yes? Yes, optimize m of x, exactly. So we're going to optimize m of x. So we just take, if we find such a thing, so the idea is we optimize m of x to find xk plus 1. And here's the cool thing. What do we know? We know that f of xk plus 1 then, in this case, say we optimize m to get xk plus 1. We know that f of xk plus 1 is less than or equal to m at xk plus 1 because this is true for all points because m is a global upper bound everywhere. So we know that inequality. We know m of xk plus 1 is less than or equal to m of xk because we're minimizing m to get the next point. So of course it has to be below whatever m of xk was. Everybody with me? And this thing is equal to f of xk. This thing is equal to f of xk by definition because it's tight at that point. So overall, we have f of xk plus 1 is less than or equal to f of xk, and actually you can show that it's equal exactly when your point is stationary and that your gradient is 0. So just to, should I hand over to you or should I say one more thing about the step? I say one more thing about the step. So one thing, we can actually write down an explicit form for this mk for any continuously differentiable function. So we can just say that here's your m of x. So I'm going to put a little k here so you know that it's indexed at k. M of k of x is equal to f at xk plus the gradient of f at xk transpose x minus xk plus L over 2, let me say beta over 2 norm x minus xk squared. So basically, we take the tangent line approximation to the function, and all we need to do is we need to add a quadratic term to that tangent line approximation that's big enough to make sure that this thing is everywhere defined. So one way to get this beta is beta should be bigger than or equal to the Hessian, so I'm not going to prove this, but I'll just tell you, the norm of the second derivative of the g function times the norm of the A matrix squared. So you probably believe this without too much derivation. The linear map plays a role, and the second derivative of the modeling function g also plays a role. If you can pick a beta that's big enough, then this thing is going to be globally above your function. And then in that case, the alpha here, you can actually replace it by 1 over beta. And so that will guarantee, that algorithm will guarantee to head downhill every single time until it stops. What's the relation between what? This g is just the second derivative of the function. So here the second derivative of this function, and in the standard case, so if you take g to be g of theta I to be 1/2 theta I squared, then g double prime is equal to 1 everywhere. So this is the basic case. In the general case, g is just the second derivative. I think I'm heading over to Peng, and then I'll let Peng fill in the remaining details.
All right, could you, neck check.
This mic is a recording device, so just speak loud.
Okay. So for the gradient descent, actually, Sasha talked about its really fundamental algorithms for smoothing optimization problems. So you can think about a surface, and then you have a little like a little. You guys play the glass balls, the things when you were a child. Anyway, so there is a point. There is a ball actually can roll down the hill, right? So what driven the ball actually go down the hill is the gravity, the force. So this gradient descent actually want to simulate that. So the gradient is sort of like the direction actually where the function value will decrease the most. So that's the thing. So, but the gradient descent, the thing is, like when we add one point, we only know the local information, and then the local information is the gradient, right? And then we do not know the global information about this function. Otherwise, we can directly figure out where is the global minimum. So how do we use that local information actually to guide our algorithm to find where is the minimum? Is that we need to find approximation locally, and then using that approximation to find where the next step we're gonna go. Does that make sense? Right, so you guys learn about Taylor series, right? Taylor expansion, Taylor series. So if we locally know what's the function value, what's the derivatives, what's the Hessian, we can naturally just use the Taylor series. So that's what Sasha right here. This is like the first two terms, right? It's basically function value and then Taylor series. And then that's a locally approximation, which is the straight line here. But it's not good enough. If we have this straight line, what's the minimum of this straight line actually? If you guys could say. Right, and negative infinity, right? We just go down the hill and it never comes back. So in that case, we need have more information about this function. So that will corresponding to the second order derivative of this function, which we refer to as a Hessian. Where you can just think about this as just a second order derivative. So if we have a upper bound of how large the second order derivative, which is the curvature information, such that we will know that we have a better approximation other than the straight line. In that case, we can figure out what is the step size, and then using that step size to recursively find what's the global minimum. For convex case, we'll find the global minimum, but for non-convex, we just find local minimum. Does that make sense? Right, so that's it. So are we gonna go through the derivation
Or
No, we're low on time. So I think maybe just show the
okay.
examples.
Okay, sounds great. So. Yes, that's actually a really good question. How to find the upper bound of the second order derivative? This is really problem dependent. So for the logistic regression, first of all, you need to calculate what's the second order derivative. You need to calculate what's the Hessian matrix. And then once you obtain the Hessian matrix, you can compute what's the largest singular value of the Hessian matrix using that as the upper bound. Right. That's the. But if you think about a scalar function, and the second order derivative just a scalar, right? And then you need to find out what's the maximum of that scalar function. That makes sense. All right, but because the only take-home message is this one is better compared to the linear approximation, and then we can use that to derive a really nice simple algorithms such as the gradient descent. All right. Show. Down. Yes, sorry. All right, you guys can see the screen well. Okay, let's go through this. This is a little bit small. Yes, it's good enough. So, right, that's better. So we have 3 Jupyter notebooks. If you guys already download this, and then you have Python, you can just directly, and then you are using, a lot of you are using Mac, so it will be okay. Right. Could you speak? Oh, sorry. This one. You can just tap this if you are using Linux or based computers. I think Windows 10 also have the Linux kernel. But if you can go to this GitHub, if you guys are using GitHub, and then you can directly download this repository. How many of you can download this thing already? Okay. Yeah, if you cannot do that, like we can have some like office hours here during the break. Right.
Another 2 hours. It's just a kind of a warm-up.
Right, and then like in the first part, you can actually there's no to do in the Jupyter notebooks. I would just like you guys to run the thing to see what's going on. Right. Is that good? Okay, let's go through some notebooks. So yeah, especially when you take a Randy's class this afternoon, which is to do Jupyter notebook, type in, and then it will automatically link to your web browser. Yes, and then there was all the materials there. It's just click the workshop part 1. I think it says here. It's a little bit too big.
Is there a way you can move the editors from GitHub again so we can
Sorry, could you speak up? Sorry.
Yeah, is there a way you can just move the address to the bottom of your screen from the GitHub address so we can clone it?
Uh,
The one that you had in the previous page.
this one?
Yeah, if you just, well, is there a way you can leave that in the
Right, okay. Let me see. Can something like here?
Just move it down.
Yeah. This one. Is that good? Yes. All right. So in this first part, we're just gonna go through the the examples about this. Oops. The logistic regression. So first of all, you need to have the NumPy and then a matplot, such as plot the pictures and also like using the NumPy to actually program up the algorithms and then run it. So yes, let's do this. Yes. And then for logistic regression, as Sasha said, this is just basically a small recap about what's going on. So you have this maximum likelihood afterwards.
And then we actually just want to parameterize the like giving a picture, what's the probability of this picture to be 1? What's the probability of this picture to be 0? We just want to parameterize this probability by using the information about this image and also our identifier, we call it X. So we do the inner product between the image and the identifier together. That will give us the probability of is this image 1 or 0. So if that makes sense. So that's exactly the message behind this inner product. All right. And then all the data set actually is coming from the AMNIST. So if you click this link, you will go to the original AMNIST. Right. So right now there is a lot of interesting other image classification stuff. They're like CIFAR 10. They are using convolutional neural nets to do the image classification about a bird and a cat. And also there is a fashion AMNIST. So you instead of like 0 to 9, you are just distinguish shoes with head or something. So if you guys are interested in that, like this basically just replace the digits by something else. This algorithm can still be used. All right, and then this cell basically just running, just loading the data. So we have 1,000 as the training data and 200 as the testing data. There's no validation, right? That makes sense. And then also we can plot one of the images. So what's this number? Sorry, it's clearly 1, right? So that's human brain is amazing, right? And also like there's other images, it's a 0. So yeah, let's recap the gradient descent. So this is the general form of the gradient descent. If we are minimizing a function f, we first calculating was we need to have the knowledge of what's the gradient of this function at different points. So we just input the initial guess, and then our stopping criterion, because this is a convex function, there's a lot of information that actually we cannot cover in this workshop. But as a convex function, it has a global minimum. There is no, the local minimum is global minimum. And also, how do we tell it's we at minimum? That's when the gradient, that the derivative is equal to 0. So that's the nice thing about the convex function. That's why it's so popular theoretically. So when our gradient already is really, really small, close to 0, we know that we are close to the optimal point, and then we'll stop. And then that's our stop criterion, if that makes sense. Right. And then every time, we also need to compute what's the beta smooth. Exactly means that the second order derivative or the Hessian of the function, the norm of the matrix is globally bounded by the beta. So that's the model we talked about before. So every time we're just updating our iteratives, our points of guessing where is the minimum by subtracting the gradient. So we're just going to go downhill by the step size of 1 over beta every time to do this. And then eventually we'll just have guaranteed to actually converge to the minimum of the global minimum. Right, and then here is the derivation of how to actually compute the gradient of this logistic regression. I will just directly put this down so that you guys can check. So just please feel free to talk to me afterwards. Let's just skip this part, and this is exactly as answer your question, how to compute the upper bound. And then here is like 1/4 directly. First, to compute what's the Hessian, and then also how to bound this. That's all the details there. So let's just do this. This one is define what's the function of the logistic regression, and then what's the gradient of the logistic regression. That's the only thing gradient descent you need to know, and also the beta. Sorry, this is the only, yes. Oh, lambda, yes. So for the logistic regression, it's a little bit special because it does not have a minimum, because it can actually go to exponential. Let's say this exponential x. Does that have a minimum? Like exponential x. Where is the minimum? What's the minimum value of this function? It's 0, right? but you can never reach that. Does that make sense? Yes. So the same thing will happen to this, like the logistic regression. You can never reach the minimum. It will just keep going. So that's why adding this small quadratic regularizers, such that it will have a minimum. The algorithm will have an easier time to converge, right? So yeah. And then this is a generic gradient descent algorithms. So all the specifications is here. You guys can actually take a look. You just need to pass in what's the initial guess, what's the function, what's the gradient, what's the beta. We'll talk about the upper bound of the Hessian. And then this one is optional. What's the tolerance? What's the maximum number of iterations you will have? And then let's do this. And then when you pass in this, you can see that it's still not converged because this is really your condition, and I don't want to add too large of the regularizers, the quadratic part. And then this is the convergence result. So the function value actually definitely is decreasing, but it's stagnates really fast afterwards. And then the gradient descent is linear convergence supposed to be, but it's really slow. Right. And then this is actually interesting enough. I don't think people actually do this. So we actually plot what's the identifier. Remember that actually having image, we have an identifier, we do inner product, which is element-wise product, and then sum them together, right? So the identifier essentially will have the same size with the image, right? So it we'll just think about it may be interesting to actually plot what this identifier looks like. But you guys can see. So what this means is that this dark is negative, and then this bright is positive. So if it is 0, it will just maybe most of the region is times this darker region, and that will give you a negative number. And then if it is your number is 1, you are probably times this bright region, that will give you positive. So that's how the machine actually can identify is it a 0 or 1. So if it is a negative number, probably is a 0. But if it is 1, if it is a positive number after doing the inner product, it probably is 1. So it's actually kind of interesting. Right, does that make sense? All right. And then afterwards, we're just testing if we're identifying, follow the same rule when we do the inner product. If it is negative, we just call it 0. If it is positive, we call it 1. And then follow that rule. We testing on the test data set to see what's the accuracy, because this is an easy one. So actually, we have a 100% identify the 0 and 1. So, woohoo! Yes. All right, that's it. Yes. Yes. This is this set, right?
Subset.
Oh no! This is subset of subset. Because large data set will run forever. It's not good for it. Yes, I think the neural nets can only do 99%.
0 and 1 task is just 0 and 1.
Yes.
0 and 1, right?
Yes. Yes. It will be It's a lot easier. Usually people will like testing like 9 and 4. It's really hard.
Or 7 and 1, right?
7 and 1, right?
All right. Any other questions? Okay, so during the break, then you were trying to install these things and having trouble. Then you talk to your friends and come find us. So in hour 2, we're going to look at exactly sparse regularization, adding other non-smooth information to the model. And then in hour 3, we'll handle robustness via crazy trimming formulation. So we'll build on this.